Okay, well, it's the top of the hour, and I think we should get going. Just really quickly, my name is Annie Burgess. I'm the lab director for ESIP, and I'm the room host for this meeting. It's exciting to have you all here. So just really quickly, a few reminders to remember to mute yourself when you are not chatting. We'd love to have cameras on when it's discussion time. And when we're not in presenter mode, but when the presenter is going, feel free to turn your cameras off if you like. Sounds like for this crew, they're not using Slido, but they'll be communicating over chat. So please orient yourself to the chat feature in Zoom. And remember, you also have reactions and hand raises and all of that, or just the old-fashioned thumbs up if you're giving feedback for our presenters. Two more reminders that we do look for ESIP to find takeaways from each session. So there is a tab in Schedule, or not in Sketch, in Kiko Chat that says 3 takeaways, and I'd encourage you to add some takeaways from the session. And lastly, if you haven't already seen it, ESIP does have a code of conduct. You can find it in the session notes. We would encourage you to familiarize yourself if you haven't. But with that, I will say welcome everyone and turn it over to Ben.
Hello. Thank you so much. And yeah, I definitely wanted to give my thanks to the ESIP staff. It's not easy to keep the summer meeting feeling going in Zoom and Kiko Chat. You've done an amazing job of keeping it friendly, keeping our community together. And boy, do I appreciate that. So I have been looking forward to this. This is something that my colleagues and I have been working on for the past 6 months, kind of hatched at the winter meeting. And so let me start my screen share, and then really confounding Annie's idea about there's times when we're presenting and times when we're interacting. There's going to be a lot of opportunities for feedback and interaction. So keep your finger hovered over those camera buttons as you come back in. So today we're going to be talking about an approach that we're taking to controlling AWS costs for a very large data set that's produced by NASA. And really want to give a lot of thanks to my collaborators that are here in the talk with me. We're going to be passing it back and forth, kind of like a talk show. So I've got my colleagues, Don Petrovic and Greg Dawes from NCSA. John Reedy from the HDF group has provided us with some amazing support in this, and he'll be talking about some of their contributions to this. And then Ryan Kolak from Amazon Web Services, who has helped us along quite a bit. So let me just start by finding my window. Okay, so here's just kind of an overview. We're going to be telling a story as we go along here. And so the first thing we're going to do is talk about this data set that is produced at University of Illinois. And then there are some real challenges with hosting this in AWS, and we'll kind of go into that. And then our solution is this data carousel, which we're going to talk about the architecture and show how it helps you really reduce the cost and also, most importantly, kind of control it so that you have a budget. We're going to show you the prototype that we've put together over the past 6 months. And then at each step along the way, we're going to be looking for feedback, and certainly at the end, like, what do you think? What direction should we take it in? So I'm going to start off, hand the microphone over to my esteemed colleague. Oh, no, I'm not. I want to say, here's just like if you saw the box for this talk on the shelf at the grocery store next to the empty shelf of toilet paper, it would say that we're trying to create a process that runs on a fixed schedule to efficiently restore specifically required data from Glacier and make it available to user-supplied batch jobs. So that's what the data carousel is. And so if you're interested in buying one of those, you come to the right talk. So now I'm going to hand it over to my esteemed colleague, Greg, to talk about the data set a bit.
Okay, so I'll introduce the TerraFusion dataset. So this is what we're using for our prototyping work. And so here we're really talking about the work of Larry DiGirolamo's team done in collaboration with the HDF group. And that was done under the funding from NASA Access. And so at a high level, what TerraFusion is bringing is it's bringing all of the data from the 5 instruments of the Terra satellite all sort of brought together into a common format and structure. And so for each unit, for each file of the data set, so data from the 5 instruments will all be in the same file if it's available. And so the full product of the fusion effort then is these 84,300-ish HDF5 files that span the observing from year 2000 to 2015. And the full data set is over 2 petabytes in size. And it's structured so that each file has granularity of a Terra orbit, where Terra orbits are like, they occur, say, about 14 or 15 a day. So that's about 450 per month. And they're not all the same size. They are in a range of about 15 gigabytes to 50 gigabytes. And that range mostly depends on the availability of the high resolution Aster instrument data, where Aster takes more data in daytime viewing. And so how was this generated? Well, it was a very time-consuming, laborious process. And so part of the benefits of TerraFusion is it eliminates the need for other people to repeat this process. So data was gathered from the NASA DAX, and gathered is probably like a gentle term. That was a significant effort. It took months, and it was done in coordination, with the DAX to speed things up as best as it could be. And then, in addition to gathering all the data, there had to be resources to handle data of that size. So this was brought to the Blue Waters supercomputing system, made use of its scratch disks and tape archive. So with that data and those resources, the fusion system executed, and then finally the results were transferred from the tape system all the way to the AWS S3 final landing place. So overall the benefits, some of the benefits then of TerraFusion are that it saves this effort for gathering all the data. And by bringing everything together in one place, it allows for synergistic use of data of multiple instruments sort of in a single analysis. So yeah, let's go to the next slide to sort of see some demonstrations of what people have done with the TerraFusion. So this first slide just shows how NCSA's visualization team was able to make some nice visualizations, all from like a single fusion file, show the 5 instruments. And stay on the next slide. This is an example of sort of a more advanced usage where open source software that the Illinois team developed can run on top of the basic fusion data, and the basic fusion data has the instrument data at its native resolution. And in this example, the analysis codes do reprojections of one instrument's grid onto another's. And so there are tools for working with this data that can bring these various instruments data sort of together and work in a synergistic manner. So that's sort of our summary of TerraFusion. And so we can sort of stop there for that.
Yeah, so before we move on, are there any questions about the data set? It's quite an interesting data set. We'll just pause for a second, see if anyone has comments. Feel free to just unmute and jump in if you don't want to type.
This is Rob Casey from Iris. Thanks for the start of this presentation. I'm curious, in the move to the AWS system, was this resampling and reprojection a necessary step? Did you need to regularize everything to something uniform in order to have an effective storage strata?
I think no. So I think that the resampling and reprojection, I think, is an analysis mode that is post the basic fusion that is in AWS. So the data in AWS is at native resolution, and it was sort of just, I think the challenge there is that it's like all in HDF5 now, where it used to be in a few different generations of HDF4, and so there are, or the granules were not uniform. So Basic Fusion has made sort of a common file format and some uniform granules, but not uniform resolution or anything like that.
Okay. So any other questions about the data set? We move on to what's this all about? Okay, so now I hand it over to Don Petrovic, who knows what the resource keeper is like.
I want to go back to the birth story of the basic fusion files, right? Is to really enable science. The story that goes with the project is to assemble the whole all time up to 2015, and all instruments from Terra is a task of assembling about 1 million files. And the real center of study is things that are called large or mission scale, which implies looking over the history of the Earth, over the series of observations, and looking over a great amount of breadth of the Earth. And so one of the motivations is, if you send a student to do something that's approximately that, the students spent all their time data wrangling and pulling it all together. The point of the project was to enable large or mission scale projects without all the preliminary data wrangling, and therefore enable science instead of enabling data wrangling. And in practice, the claim is that the science of this scale would largely be forgone and not done because the overheads of getting the work done were just too high. So a common base of information is supposed to enable new types of research that people just wouldn't do because they couldn't get over the mechanics of assembling the data and doing it all, assembling all the data. Let's just put it that way. So on the other hand, all of this enables science to be done, but 2.4 petabytes is a lot of money, right? If you think about just hosting the results, you would expect to space, if you wanted to put it in S3 standard, which would be the easiest thing to do, you're kind of in the $600,000 a year list price regime. And probably you've got to have an additional backup copy in Deep Glacier, because what if someone fumble fingered and removed the objects or something like that? If you're going to spend that kind of money with a data set, the trouble is you need to demonstrate that there's a large science potential and a substantial user community that require, things that traverse time, things that traverse a large area. If you're just going to go look at a small patch, the current system of DAX is probably just fine. So in practice, this kind of begs a chicken and egg problem, right? If you're claiming that there's a large amount of research that can be done by looking at the system of the Earth comprehensively in both time and over the surface of the globe, people that have that kind of money would kind of like proof. And so how do you show that there's demand and simultaneously being faced with this kind of bill? And so the rest of the talk is actually can be viewed as a bit of how does one solve this chicken and egg problem? how does one all of a sudden make a large data set like this useful? And then one is able to afford to host it, and then be able to demonstrate the scale of use, and therefore be able to begin to understand the level of resource support the data set should have.
All right, so $600,000 a year to store this in S3. That sounds hopeless. Ryan, do you have anything that you can offer us?
So AWS, yeah, this is exactly where AWS comes in, right? So I'm going to spend a little bit of time explaining the basics of our simple storage service, or S3. So if you've heard of, if you're familiar with some of that, this might be a bit of a review, but it's really important to understand the benefits that you get along with S3. Mainly that there are multiple copies of your data that are stored across multiple locations within a region. So that's how we're able to drive towards having 11 nines of durability, to make very, very reliably to be able to store your data within a scalable, unlimited storage facility. So also, AWS will automatically scale up based on the demand that that the individual objects are being used. So multiple copies will get made so that there's additional bandwidth to be able to serve that out. And you're only stored for the size of the single object that you're storing, not for all the copies that are included with that. So oftentimes people don't necessarily compare that when they're looking for another solution. So it's important to keep that in mind. But on the left, Don was talking about S3 standard. That's kind of where people tend to start. It's data is readily available. It's easy to access. But then as you move closer over towards the center, you start getting into some more specialized storage classes that are specially designed for certain use cases. So for example, the S3 standard infrequent access, that's what the IA stands for, is designed for data that is not going to be accessed very often. So you can think of like assets on a news archive site, right? After a certain period of time, they don't get accessed very often. So you trade that storage cost and are charged an access fee whenever you access that data. So if we jump all the way over to the right side of this slide, we start talking about Glacier and Deep Archive. So that's really designed for data that is meant to be stored for the long term and doesn't need to be frequently accessed. So this project kind of turns it on its head a little bit because we are frequently accessing that data. But what makes the advent of the Glacier Deep Archive storage class that offers storage as low as $1 per terabyte of storage allows us to do some really interesting things. So of course, to get to that price, there's a couple conditions and limits on the way that we actually access the data. So those are over on the next slide. So first, there's really four main things that that we had to consider within this project. So there's two types of retrieval tiers. We're interested in limiting our costs, right? So before you can actually access the data, you have to request for it to be restored. So for you have your choice between a standard retrieval or a bulk retrieval. So the difference is it's up to 12 hours for standard or up to 48 hours for the bulk. And since we're happy to wait that time in exchange for the reduced price of $0.25 per gigabyte to restore that. Additionally, there is a copy, that restored copy. You get to choose how many days you want that to be available for. And then you can delete it earlier or it will expire after that period, after that time. So there's a 2.3 cent per gigabyte charge for that restored data as it's available for access. So again, not relevant to this project, but there is a 180-day minimum of storage. So if you delete it before that, you will be charged for the remainder of that time period. But most impactful for some of the design decisions we have is that there are 35 restore requests per petabyte that's stored within Deep Archive. So that really shapes a lot of things that on the next slide we get into kind of how those actually break out. There it is. So oh, okay. This was actually updated in the slide deck, but it's not quite there. So it's actually 35 requests per petabyte, which means that on on the scale of 2.4 petabytes, that's 84 requests per day that we can make. Also, there's a maximum object size for what can be stored within S3. So it's 5 terabytes per object. So, so if you think about that, that means that if you're able to make 35 restores per petabyte per day, and that's 84 restores at 5 terabyte objects, it's going to take about, that 5 days should be 14 days. So it's about 2 weeks to get through a full tour of the data. So I'm sure that we'll update those slides before we make these available. But that gives you, so that means that we have to pack related files together into a single archive so that that single object can be retrieved, because that's the unit of everything within S3 is an object store. So we're working with a single object at a time. So so a lot of work had to go into that, which we'll be talking about as well. So, and then again, this has the note here that there is access for up to 24 hours. And since we go ahead and actually are able to leverage the other resources within AWS, it really gives us a good platform to make that data available in a standard storage so that it can be accessed by other AWS accounts to allow people to actually do the science on that data. So that's the intro to S3. And unless there's any questions, we can.
There was a question in chat, is whether the deep archive backed up to assure no loss.
So when it comes to backups within S3, because there are multiple copies of the data that are stored, so you get that that redundancy built into that. So so like Don was mentioning earlier, that there still is the concern for if someone were to accidentally delete that. So you may still have another copy sitting somewhere else, maybe in another region or another account that's protected. But as far as from a preventing against loss within AWS, that's achieved by the multiple availability zones. The human oops requires some more protections from the security tools as well as the replication.
How many nines? Does Glacier have the same number of nines?
Yeah, same number of nines. So on the slide that had the various storage classes, there is a one zone, so that you can basically choose to, for a reduced cost, you can choose to have a single copy available. So it's not replicated to multiple availability zones, and that will only give you 4 nines of availability because you don't have an additional copy. So typically that's for things that are transient data that you can regenerate without concern.
And Evan has what was definitely one of our common questions as we first started the project is, what does frequently accessed data mean? What are the guidelines for that?
Yeah, so as we're talking about things like, so that infrequent access, you end up normally, or so the approach you take when you're trying to determine what storage class to use is you project what the likely number of accesses that you're going to have. And then you can compute based on the 1 cent per gigabyte access fee that there is for the infrequent access in exchange for the 1.5 cent gigabyte storage that you're paying. So if it's very unlikely that you're going to access all of that data, then it certainly makes sense. Unfortunately, the answer with AWS very often is it depends. So it depends on what your data set is and access, but you can easily model it. And one of the other tiers that's on there is called intelligent tiering, which will automatically move items between infrequent access and standard storage. There's a management fee for that. So you, if you have many objects, that may not be cost effective, but for things that may suddenly get popular, because if 1,000 people access it, you'll pay that access fee 1,000 times. So intelligent tiering can move something that gets access over to standard tier, where it can then get moved back.
Okay. Any other questions on Glacier and Amazon storage? If not, we'll. All right, Don. So now that we know about Glacier, how does that change things?
You can see that what you're going to trade off is the cost of storage and data movement for you to be able to view it versus having to work in a batch environment and plan. The first thing that you have to say is, to go back to the first slide, is that if you don't have all the data and you need all the data to do your science, you're going to live with the limitations of the technical solution. But is that really so bad? first of all, if you're going to really try to go over something like the whole data set, that scale of analysis is more like measure twice or 4 times and cut once, and doing small runs that you've parked on the side. When you go and ask earth scientists available for me were people at Illinois, and they said, well, if you're trying to do something with a data set that big, how frequently do you think you might want to run over all the data set given there was a constraint? And the answer comes back sort of like every 2 weeks. So a large analysis, giving a scientist side copies of sample data to debug their software and think a little bit as they revise it, and giving them a chance to look at the data every 2 weeks would be an acceptable platform for scientists doing science, and make something like a data resident on tape feasible. When you say that we do it on AWS, they also start saying, oh yes, I must conserve my analysis budget as well. And running over that size data set costs at least tens of thousands of dollars. Also, then you start saying, well, you'd have to not quite have the granularity of files that you might have on a POSIX file system, that we might have to pack them, but we can give you some abstractions to mitigate that. But there is work to pack it. That also seemed acceptable because it's kind of do it once. Lastly, when you start mentioning that people pay to fetch each time, once a science group grows over a couple of people that couldn't coordinate among themselves, then it seems necessary to have some sort of software to orchestrate the staging request and the job dispatch needed as each file arrives, in order to save resources overall, and just basically provide a kind of framework that is practical for a scientist focusing on science to use, as opposed to a scientist trying to stage the files in a minimum number of times. We can go to the next slide.
I like the quote from Joe in the chat. If it takes me a month to understand the results of a query, I don't care if it takes a day to run. So that's probably a lot of this world.
Yeah.
Okay.
So you know, what is such a system? And there's a figure on the left-hand side. Is that the idea is that, first of all, when files are ingested into this thing, they're built up to something like near the 5 terabyte limit. The 5 terabyte limit and the size of the data set with the number of stages allowed today set an ultimate speed limit on how fast you could spin through the whole data set. And I would say that given the insight that 2 weeks is enough, when you work it out for the basic Fusion toolkit, you get order of a week to spin over 2.4 petabytes. So our speed limit is not technically limited by the number of times we could go through the data set. It's limited in practice by how fast a scientist would really want to work on a whole data set of that scale. The idea is that in the top orange, can't point with my pointer, the very top part of it, I show you a Carousel request server. And the idea is that people there would actually make requests for the files they want. And so it's not necessary to go through every darn file if every darn file isn't requested. But basically you're sitting there and you're kind of batching up stuff and knowing what the user community wants. Based on the queued up requests, the Carousel stages up whatever Ryan said, and that's not quite 50 files a day, right? And the files are available. And what happens as a property of S3 is an economical way of running the Carousel is the files are now available once they arrive for 24 hours, right? As the files are staged up, the Carousel signals now that code should be run against them. Scaling the amount of compute is not a problem if it's done in AWS because you have an elastic compute capability. Right. And after 24 hours, the file reverts to inaccessible. But what is also very important about this drawing is that the staging, so the function in orange, and all the files that are represented as in this black zone are the responsibility of the data carousel and the data carousel operator. So the data carousel operator pays the transfer costs to bring the data up to a usable state and notifies the end users using some sort of notification method. And the user analysis runs on their own infrastructure and on their own budget. So you're able now to all of a sudden separate the costs of the operator of the carousel, and each user would be able to pay the cost of their own analysis. And in a case where you're a data center or a data service provider and wanting to safeguard your own budget, this allows a kind of very foolproof way to understand your costs, which relate to how often the cadence you run the carousel and what fraction of the files are requested on an average run. And you have totally decoupled yourself from any costs the users may incur. And lastly, this sort of system works for any kind of file. We happen to be using HDF5 files because that is the implementation choice of the Access project. These files could be any sort of file. It could be some sort of gigantic COG file or package of COG files. And so this part of the system is robust, works with many kinds of file types, is agnostic to file type, and represents infrastructure that if you build it once, you have one kind of data service that can service many types of files, and in fact can serve many types of projects if you really understand that the staging limit of n a day goes to the petabyte volume that you have, and is not in any sense an absolute limit for any AWS customer. It's not 40 a day for any AWS customer. The staging rights scale by data volume. So what does this look like to a scientist, right? The scientist will say there's key science requiring large data sets. The scientist has to say my problem is file-wise parallelizable. So you can't be doing an FFT over all data from Terra, but you wouldn't want to if you understand what it's packaged, right? You'd begin to say something like, this is the only way I can get science done. You'll scratch your head and you might say, you know, I used to do this on supercomputers and I had to wait for tape staging anyway. So, you know, how is this any different than what I've seen before? And in fact, it might be a little better. Tape staging in a supercomputing center sometimes involves undeterminable delays that cannot be determined. Here, the delays are as Ryan indicated in his talk, more or less bounded. So, you know, the other thing, as I said before, I need to carefully ration my budget anyway. I can't be burning through it. I have to think about it. If one run doesn't do, I've got to stop and really think hard about a bunch of improvements for the next one. But what's important, you know, I think if you own a data shop, if you're in NASA, you own a data shop, people like to throw this Anti-Deficiency Act, which is you can't spend more for data service than you had budgeted for it because Congress doesn't want you to incur unbounded expenses. The news here is you can budget, right? If you run a data carousel, your data movement and storage costs are capped at the sum of the storage plus the maximum numbers of full turns that you'd allow people to have at the data. And we have this heuristic that about every 2 weeks is fine, right? In particular, you're in the very nice situation that you pay the staging costs and the users pay other access costs, including these pesky little small per whatever charges that are mills or worse, but wildly badly written software could run up a bill. The maximum cost is less than a third of a cost of S3 hosting. And I used as my basis of estimate the more prompt staging. If you wanted to go to the even lower cost staging that Ryan mentioned in his, the cost will come down considerably, and there's a slide a little bit later where I'll discuss that. You also get management information for your data set. Because people request things through the data carousel, you have a per file, per user view of interest in the data set. So now all of a sudden, instead of putting it out there on S3 and wondering who's accessing it for what purpose, you begin to have a grip on another level of information that will let you manage your data. Another benefit of the carousel is if the use community is large, they do not need to communicate between themselves. They simply talk to the carousel and have to wait for their files to appear. So there's no coordination among people trying to save the staging costs or any such problem. If you're a proprietor of this thing, you get to rub your hands together and say, I save some money every time I make a run and a file isn't needed, because you're saving the staging costs. And also, you all of a sudden are now not in the business of trying to judge how I shall store this in what tier, because if interest in the data set declines to 0, your cost decline to the mere hold it in deep Glacier, because you're no longer doing any staging. And so your budget is also sensitive, and you obtain savings based on the level of interest in the data. And lastly, as I mentioned in the previous slide, the carousel software itself is reusable and applicable to many data sets. And so where you do come into sort of long-term maintenance, it's maintenance of a framework that can be applied to many data sets. It's not maintenance of the data set itself.
So maybe we should do the next slide that has some interesting stuff on it before we get to some of the questions that are in there. Oops, come back here. All right. So the tables of numbers. Go ahead, Don.
Okay. So okay. I guess I made this too expensive. So on top is the first 3 lines in white are what you would pay for the 2-week tour through various storage mechanisms, approximate S3 list costs of 3 or 4 months ago when I pulled the table together. S3 is on the order of $600,000. S3 in frequent access, if you're going to really go through it 26 times, is higher. Glacier itself is at $270,000. And the deep Glacier cost I put down for various levels of use. And if you're actually willing to use the mechanisms where the staging cost is less, those numbers decrease by at least half. And so now you're down into some tractable amount of money to provide data service to experimenters. And you're also in an environment, as I try to show you with the different levels of interest and access, you're in a part where your budget simply scales with access and scales to an absolute maximum value. Right, this is a property that you really want if you're going to offer data service.
Okay, thank you. We have a couple of questions in the chat. One of them is about the size of the S3 granules. So if you make them smaller for maximum restore flexibility, or is it better to store large granules?
So,
and these are fun questions.
Yeah, it is best to store, in my opinion, large granules, because you need to remember, one of the limitations is the number of restores per day, which scales with data size. And so the right process is to think about the speed limit of touring the whole data set, if your goal is to provide access to the whole data set, about how fast you could possibly accomplish that. That in turn drives you to the number of the number of restores per day drives you to how big you have to pack the files. You can pack the files, with some work and some magic, you can pack the files into something like what I would assume to be a non-compressed zip format and write the software to decode that and find files. I assume it would be a non-compressed zip format because I think anybody in the petabyte business is presumably compressing their data already.
And this is one of those things that it depends on the way the data is accessed. So if it turns out nobody ever wants the entire data set, but everyone wants little pieces of it, then you're much better off with smaller granules because then you're not touching everything. But if you have people that want the entire data set, then you run into trouble if your objects are too small. And so as we've been playing around with this, we see that there are so many knobs and dials that can be adjusted depending on how the data set gets used. We'll talk about a few more of those.
Yeah, it turns into kind of a scheduling thinking about scheduling
Yes.
at its base.
And then we'll undoubtedly get to this question later, but I'll just put it out there from Jeff. Can the carousel provide notification to subscribed users when files are staged, potentially accommodating multiple users with a single request? And so, yes, that is the architecture. In fact, I'll move to the next slide. And so, so that's what we've been trying to build, and we've been spending the past 6 months working with AWS tooling in order to create a proof of concept. And so here's the high-level architecture diagram of what we've actually built. And so down here is the happy researcher who gets to work with this data. They submit a request through the API gateway, which just records the request in a simple database. And then there is a tool called Amazon Event Bridge, which is like cron. And so it basically spits out events on some granularity. And so we've told it, okay, every 2 weeks, send out a message which starts restoring the union of all the files requested by the different researchers. And so then that just goes off and it runs at whatever speed that it takes. And eventually these objects are restored into S3. In the meantime, so we're using a service from HDF Group that we'll be talking about in a second called HSDS. And we've indexed all these files and the metadata sits in S3. It's a much smaller data set, and that's always there. So the data is very easy to access it. And so then as files are restored from Glacier, we kick off a Lambda function that says, this file is now available. It looks at all the jobs that have subscribed who are interested in that file and puts it on their work queue. And so this box down here is basically the data carousels, virtual private cloud, and our bill. Up here is each researcher's bill. And so they have their own HSDS server, which we'll talk about in a second. And then they're using the Elastic container service to run their jobs, pick stuff up off from this work queue. And so, Jeff, yes, there's a job queue for every researcher that submitted a job. And so they all get notified as soon as that file gets restored. So I think we talk next about some of the challenges of using HDF5 file formats on S3 and some help that we're getting from HDF Group. John.
Hey, so we've talked a lot about the mechanics of how Data Carousel moves these files from Glacier to S3. Now let's talk about the problem once you have these files in S3. You could, once your file shows up on S3, you could download it. But since these files are typically 50 gigabytes or 4 terabytes in the case of the concatenated files, that's quite an inconvenience for the researcher. So it would be nice if you could access this HDF data as it sits on S3. And in fact, there are various ways you can do that today. For the H5 library, we have a low-level driver called the S3 VFD that lets you do read access to HDF5 files stored in S3. There's also a virtual file system called S3FS for Python users. There's a thing called a Fuse file system that creates like a virtual network share out of an S3 bucket. But the common problem of all these techniques is that they are just very slow in practice. And the problem is that the HDF5 library was originally designed to access POSIX files, typically on local disk. And when you replace latency of doing a local disk I/O with a latency of going from your local computer to S3 and back again, that becomes much slower. And the way the HDF5 library works, that typically when you're doing an API call, it's going to be seeking around various places in the HDF5 file. And so each of these seeks is an additional latency to S3. And so the cumulative effect is that it may be tens or hundreds of times slower than dealing with local files. So thankfully, the data Carousel team got in contact with us, and we collectively decided to use this our new product called Highly Scalable Data Service, or HSDS. And we'll talk about that in the next slide. So what it is a REST-based service. So rather than the HF5 library being a library that your application links to, it's a service that you connect to through this REST endpoint. And it can be run either as a set of containers in Docker or a set of containers on Kubernetes. And the more containers you have, not only can you support more throughput, but also the performance of individual requests scales up. So when you have say a data selection request that spans multiple chunks, HSDS can run those chunks in parallel across multiple containers. And each of those containers can be doing requests to S3 simultaneously. So you get much better performance with more containers. And Kubernetes is nice because you can actually have a whole cluster of machines running containers across multiple machines. And now not only have more CPU power, but also you have multiple data I/O pipes from each of these containers running on their system to the S3 storage servers. So HSDS is generally faster. How much faster? Well, it depends a lot on the way the file is structured and what usage is. But it can either go from being moderately slower than accessing local files to being even faster than accessing local files. And the reason this is because you're reducing the number of S3 requests, right? So when we ingest HF5 data into this HSDS metadata bucket, we're consolidating various pieces of metadata in the HF5 file to single JSON objects. Another factor is that the server caches recently accessed data. So a server might have gigabytes of RAM devoted to either chunk cache or metadata cache. When that data is requested, it lives in the cache, and then subsequent requests would only need to go to the cache. They don't need to go all the way to S3 to fetch new data. And as I mentioned, data can be parallelized across multiple containers. And one thing Don was pointing out is that the data Carousel team, the plan is to ingest the entire 2.4 petabytes of Terrafusion files into this HSDS metadata. So that metadata will be available all the time, regardless of whether your actual file has been loaded from Glacier to S3 or not. Okay, so that's fine if you are comfortable using REST APIs directly, but many of us are using Python or C++ applications. For Python, we have a package called h5pyd, which basically mirrors the h5py Python package for the HF5 access. And for C++, there's a plugin to the H5 library called the Resval that, again, lets you interact with content managed by HSDS the same way you would work with local files. And ideally, you won't need to make any changes to your code, right? The same Python script or C application would just work with h5pyd or with the Resval plugin. There's another interesting aspect is that since there is a REST API, you can code up some pretty cool interactive web applications that would use JavaScript to directly access the server and fetch data and display it graphically. And I'd like to mention that HSDS was developed under NASA Access 2015 project. Okay, next slide. So I want to talk a bit about the HSDS data schema. So it's basically a sharded schema where we're taking the contents of an HDF5 file, the chunks, dataset types, links, and so on. And we're storing those as JSON objects. And then the chunk objects stay as binary blobs stored in S3. So if we have a dataset with 1,000 chunks, you'd have one JSON for the dataset metadata and up to 1,000 S3 objects for each chunk in the dataset. So the nice thing about how this is laid out is that the service doesn't need to have a content directory or listing objects to fetch the object it needs, right? It can just deterministically find the S3 URI to the object. And if it's not there, it assumes, like in the case of, say, a dataset chunk, that that chunk was just never written to, right? So in HDF5, when you create a dataset that's, say, 1,000 by 1,000 elements, you don't allocate space for all those elements all at once. You allocate it as you write to individual chunks. So if we take the 84,000 Terrafusion files and we convert those to HSDS, it would be quite a challenge, right? Because you'd be processing 2.4 petabytes of data and reconverting all that to the schema, and you'd end up with another 2.4 petabytes of data you would need to store. So rather than converting all the data, what we do is just ingest the metadata. And then the chunk information we leave inside the original HDF5 file. And the metadata contains pointers back to this, basically the HDF5 S3 URI, an offset into that object, and the size of the chunk. So as the server needs to access the chunk, it can do what's called S3 range get, basically pull out that chunk from the original HDF5 file and return to the server, and then the processing works just like any other chunk for the server. And so all this happens without any interaction with the HDF5 library, at least on the server side. And it's quite fast because we don't need to go through, again, through the whole pipe of indexing into HDF5 files that you normally have. All right. I think that was it for my part.
So first off, are there any sessions later on at ESIP?
Oh, yes, I was going to mention that. Yes, I'll be talking more about HSDS at the HDF Town Hall tomorrow morning. So if I've piqued your curiosity, you're welcome to attend, and hopefully I can do some demos with some of the Terrafusion data as well.
Okay, and then as Don mentioned, we use HSDS because our data set is HDF5. We can consider plugging in other things like ZAR or other things depending on the format of the data that we're accessing. So Peter Groves had a remedial question, probably for Ryan. Is bandwidth free between two AWS accounts? Haha.
So yes, as long as they are within the same region. So that data, the data transfer cost is so within S3, there is, since the data is, there is bandwidth between availability zones within a region, but since S3 stores copies in at least 3 availability zones, you're able to pull that from wherever your compute is. That's a local transfer within that. So there are things, so there are other charges like the API costs, and those are all borne by the requester pays to push that over to the people who are actually consuming that. So,
and then
yeah,
Joe's question kind of gets into a bit more detail because we'll show this in more clarity. But what we decided in our architecture is that every researcher runs their own HSDS, so they're paying for the compute costs, and so the boundary is between the HSDS server and S3, and so you, the researcher, you're going to be running your own HSDS server on an EC2 instance, and then you're only getting paying for S3 access.
Right, and it also it kind of highlights an explanation for the second part of Peter's question. Is there any difference between accessing S3 objects versus REST calls? So your client application with making a REST call to your HSDS server, that HSDS server is making S3 calls to S3. So in the end, from the VPC to the other VPC is purely S3 requests going out.
Yeah, and those requests are also, by its very nature, the S3 requests are API requests themselves. So it's just a standard HTTP request that's going and retrieving the file. It's made more efficient by doing that ranged get just for the pieces of the file that you're interested in.
To split a hair, the running the HDS server is on the application side. If the application knew that it had in turn had several sub applications that wanted to share one HDS server, the application could be constructed that way.
Yes, for sure.
And you could on the same EC2 instance you're running your application on, or you could have a separate instance for a server, or you could use Kubernetes and have a set of EC2 servers and another set of applications making calls to that server.
Okay. Any other questions about HSDS? So next we're going to talk about, maybe a lot of people are familiar with batch in like HPC centers, but how about running batch in AWS? I'm sure it's different. How about it, Ryan?
Yeah, for sure. So, there's a handful of services that we're actually using within the solution. So we touched upon SQS, the simple queue service, and really it just allows you to pass very lightweight messages to a queue very inexpensively, and you don't have to manage any brokers and any of that hardware. It's just a service that's provided to you. So one API call to go ahead and write a message to a queue, and then you can use that. The destination queue is going to be in the individual researcher's AWS account. So that the presence of there being an item in the queue can be what triggers the events to actually go ahead and kick off and begin to process that data. So, and it really does provide that really simple interface that you can actually have, establishing the contract of what the interaction is between the data. And we wanted to make it as simple as possible so that we're able to just kind of let people know that their data is available, and then they can do whatever they want with it. And then that 24-hour clock starts from when that message drops in the queue. And Don mentioned it earlier about how you have access to elastic compute resources. So EC2, of course, our elastic compute cloud forms the basis of everything within AWS. And of course, you have many options of how you choose to actually architect your application. You can choose to just launch EC2 instances and run your own Docker containers on them and manage all of the infrastructure yourself. However, there are tools that actually make that a little bit easier. So in our sample solution that we worked through, we used ECS, the Elastic Container Service, because what that does is it provides a very simple interface for going ahead and actually launching tasks, one-off jobs, or services, which are long-running sort of applications. So if Kubernetes was also mentioned, there is, so EKS is the Elastic Kubernetes Service. So allows you to actually run a managed Kubernetes as well. So you don't have to go ahead and actually manage the underlying EC2 instances. They are still available for you to go ahead and I'll process those. So the way that we were actually envisioning that is that the message drops on the SQS queue, and that would trigger a process that can scale up and instantiate your EC2 nodes and begin to go ahead and schedule the individual tasks to go ahead and run that. And since there's essentially an unlimited amount of compute capacity within AWS, you can choose to run that against, to scale up to very large instance types and run very many of them. And you also have the option to leverage things like the spot market if you're reasonably confident that you're going to be able to get through that workload. with the constraints of the spot market. That's a bit of a different topic though. And the other thing to mention as well is that both ECS and EKS offer the option to use what's called the Fargate engine behind that. So, so what that is that's essentially running a, choosing to actually not have to manage the underlying hardware. So you're able to go ahead and not worry about having to pack and make sure that your nodes are being fully utilized, and you just pay for the duration of when your container actually runs. So there is a little bit of a premium for that. So if you're able to fully pack EC2 instances, I believe for most instance types, the break-even point there is about 80%. So if you can keep your nodes about 80% occupied, you're going to be able to go ahead and achieve a lower total cost by leveraging ECS on EC2. However, the flexibility of being able to just launch a container and not have to worry about spinning up a node to run it on is also very attractive. So, and you can mix and match between various tasks that can run on, can target various clusters that either are served by the EC2 backed nodes or running on Fargate. So, and I believe that, I think that covers everything that we're running here. Yeah. So, yep, on to the next.
Hey, yeah, any questions about batch and compute on AWS? I think people are fairly familiar with that. So now we're gonna dive into what we built and kind of what okay, what does it look like to operate the data carousel? And so in terms of user serviceable parts, there's two pieces. There's how you submit a request and then how you deploy a job. And so requests, we have a REST interface. Someday there will probably be a Python library that makes it easier, but for now it's just a REST interface. And then for now, we are imagining that you would deploy your code in a Docker image. And as we said, it certainly runs in your AWS account. So we've got this set up. There's a API gateway. And so here's an example of the crudest possible job submission. And basically, you're saying who you are, you're giving it some sort of description so you can figure out what this is when it finally runs. And then there's like a query, and it would probably be more sophisticated at a later date, but for now it's just basically the where clause of a select statement that says which files am I interested in. So I submit that to an endpoint, and I get back a response that says, thank you very much. That query picked up 233 files. Here's your job ID, and the train departs the station on the 20th of July at 9:18. And so pack your bags. And so then at that point, you have until that time to set up your job environment. And what by convention, what we do is as files get restored, we put notifications on a queue that's named after that job ID. And so as a researcher, you're responsible for setting up a queue that has that job ID, make it available so that the carousel can write to it. And then we've got some example code. I would say that at this point, the data carousel looks a lot like, I don't know if you've seen the robot on the Google HTTP 500 error, like the robot that's assembling itself. That's kind of what the carousel looks like, but we've got all the pieces and we know how it can all fit together. So, but you can imagine that you would have, we've been playing around with Elastic Container Service that spins up one or more of these containers, and you can have an autoscaler that's listening to these queues. And so ideally, you scale your cluster down to 0 while you're waiting for these files to get restored, and then scale up quickly as files appear to try to get through them as quickly as possible so that you aren't at the end of the 24 hours when the file disappears, you haven't finished all of your processing. And so, if there's any number of things that you could do with the results, probably the easiest thing would be you put your results into an S3 bucket, or you could have it downloaded to some home environment. And so here's a little cartoon of what a batch environment looks like. So over here on the right is the work queue. And so files that they get ready to process show up in there. Here's my Elastic Container Service. It's running, and it has a container that uses H5PyD, which is that library that makes HSDS look like local HDF. And it's reading these restored HDF5 objects and the pre-computed metadata. And then here I have floating off in outer space the autoscaler that adjusts the number of tasks to deal with when files are available and when files aren't available. And so just to complete the picture, this is what a sample message from the work queue looks like. And so it gives you, this is in the namespace of HSDS. And so there's a thing called the domain, so TerraFusion domain. This is the orbit 108, and here's a specific file. And the analysis that we're working with wanted to know the year and the month as part of the metadata. So we threw that in there. Probably this message would have quite rich metadata in it so that when you get a job, you can get straight to work. And we have like the basics of a CloudFormation template. So CloudFormation is a way that you can bundle up a configuration for AWS components, and then it has parameters that you can enter, and you just go to the the CloudFormation page in the Amazon console, and it goes and provisions all this stuff for you. So if we do our job right, researchers don't need to know anything about virtual private clouds and all the different aspects of this, but you can automatically configure this compute environment to run for you. And so it has to have inside of it your work queue, bring up your HSDS instance, and then the Elastic Compute Service with all of the auto scaling. So brings us to the reactions and community input portion of our show. So we have, actually, let me just show you. We got some resources at the end of the slide deck. We were, like every great ESIP presentation I've been involved with, we were tinkering with the slides up until 5 minutes before showtime. So we will put the slides in the sched that has these links. But we do have a GitHub with the data carousel code as it exists right now, the Docker image for ingesting and cataloging the data set, source code to the Lambda functions, and some CloudFormation templates that probably don't work. And we also have a code base that does an analysis. So, and then there's a white paper that describes in more detail what we've done and how it, what the benefits of it are. And there's quite a bit of information on the HSDS. So, yeah, so it's been a fun project, and we're looking forward to hearing some feedback from our community here and see if we have suggestions on what should come next. So I'm gonna throw the floor open at this point to discussion. Any
I'll
questions?
try to loosen it up by saying that right now, what we've achieved is a prototype that's taken us through all the steps to show the feasibility of implementing this in this environment, and that we can achieve several important goals, including the separation of cost from the data provider to the data user.
So Joe Lee, are there any science users who use TerraFusion data via data carousel? Not yet. It's not really ready for prime time, but yeah, Don was actually holding me back. One of our researchers in Illinois has he had a request for doing something fairly quickly with the TerraFusion data set. I was like, oh, we should do it in the data carousel. Don's like, careful, careful, grasshopper.
I was buying the AWS cycles right now out of my little research budget.
Yes.
So I have not converted. Like I said, my goal for ESIP is to get to the point where we can say we could finish this thing with confidence because we have probed everything that we think needs to be integrated.
So does anybody else out here in ESIP land think of some other data sets that might benefit?
I was just going to ask a question. I mean, Ben, do you feel like there are, in terms of when you guys were all making this, that this is one potential model for going forward as more large data sets make their way to the cloud, that this is showing one model of a little bit of user pay, a little bit of kind of the data repository or that agency paying, or do you feel this is really most suited to kind of a research product, like your situation where you're at a university? So I'm wondering just if you would project this through what you've learned through the project, if you do see this as a potential model for how this could work for other large Earth observation data sets.
I'll probably let Don answer this question.
If you look at the support slide, you'll see that we received substantial support from NCSA. We started this work because I was inspired by taking this very old data access pattern of a data carousel that I used in years I don't even want to mention that you guys were not alive, perhaps, many years ago, and trying to apply this access pattern to attack AWS costs. I would say that the limiting of the cost addresses concerns that I had heard from NASA, and I am the technical chair of a large mission scale working group. And we were encouraged to try to do some things that are out of the box to see what would happen. And as it would happen, I had some life problems and I disappeared for several months. But this is this idea that I put out there, and everybody seemed to like it and jump on it. And I thought that we had to thoroughly prototype it to understand if it is an implementable idea. And that as far as we gotten there. We also have received some interest from the University of Illinois central IT people who support the researchers, because they are looking for a way to host big data in the cloud and everybody faces the same constraints. So I would say that this right now is a project that solves problems that we have heard of, but does not yet have a full-fledged stakeholder involved in it. And that is one of the reasons that we're presenting here, is that we're actually trying to say that this needs to transfer from a set of business problems where we have a technical project to understand if there's actually interest in this out there. So we're looking to say we've prototyped this idea and we've risk reduced it, but we're not saying I have a sustainable software project at this time.
But I do think it is interesting. So it's definitely interesting for large derived data sets that is difficult to pay. You know, it doesn't live on a DAC, and it'd be difficult to find someone to pay to host the data set. But I think it also might be of interest to infrequently accessed large data sets as part of a solution to, as the DACs are moving the data up to the cloud, you know, the costs are eye-watering. And if you can get away with hosting the data using the data carousel, then you can reduce your costs quite a bit. So I think I'm going to ask Jeff DLB to unmute to give us more nuance to your question about about data availability.
Sure. Hi. I just wasn't clear if I had heard right at the very beginning. The carousel kind of temporarily stages data. People request what goes on. And so did you say any one piece of data would live for 24 hours in this easily available thing, and then it would kind of rotate through every week? I didn't quite understand the synchronization between this 1 week and one day period.
Right. So it's a train that leaves the station every 2 weeks, let's say.
2 weeks.
I mean, and that's another one of those dials of, you know, how often does it need to run. But let's say the train leaves the station every 2 weeks. At some point during those 2 weeks, if someone had requested that file, it will appear in S3 for, and again, this is also configurable, a 24-hour period. And the only way that anyone would know that that file is there is by listening on the message queue, that you get a message that says, here's your chance to process that file. You got 24 hours, and then it disappears. And again, there's all sorts of interesting knobs of, is 24 hours the right answer? Could you make it shorter? Can you make it longer? Can you run the train more often? There's lots of different ways to optimize it.
So the user is going to know that sometime in this 2-week period, for 24 hours, the thing happens. If that happens to be the day you're, whatever, weekend on vacation, too bad, you better have your stuff set up to process automatically and then fix the bugs when you realize that your code isn't working and so it crashed after a millisecond. Or so you really have to be on top of it. It sounds like to use it.
Or there should be no human intervention. You really need to just have your containers all set up. They're listening on the queue, and you've got sample data. So hopefully you've tested it out before this thing happened.
Okay.
And we talked a lot about, so in my mind, it made the most sense that you've got code that's waiting to catch it, and it does its analysis, and then just the results get stored. Some other people were thinking, actually, maybe I want to use this as just a very complicated way of copying data out of Glacier into my local, like my supercomputing site. And so I've got 24 hours, the data is now here. I can do the copy, and then it goes away. And it could be, that may be how people use it. We don't care.
All right.
Okay. Yeah.
Thank you very much.
Oh, and then Rama has the question that I should probably just delete and pretend he never asked. Who's going to pay for this? How's it sustained? Don.
Well, I think I tried to answer that in what I said, is that this seemed very interesting to us. It seemed to be a path to big data where substantial cost savings are achieved. And it's primarily driven by people in the large mission scale data groups saying, could you think a little bit out of the box? This is what we came with out of the box. And there is secondary interest at Illinois, because Illinois is looking for a strategy for people with big data. And we're here to actually try to understand if there is interest. We're presenting the results of a prototype and the bones of an argument.
So yes, this will not last. Do not rely on this. And then we're looking to see if we can get interest into turning this into a real product.
Yeah, if everybody in the world said, go put it on GitHub and we all want to contribute to it, that would be a result. I don't know. We're here trying to talk.
And so, Joe, if AWS cost and service change will have to be re-architected, possibly, more likely, it's tweaking the knobs of, okay, maybe we can run the train more often. Maybe the files can hang around longer. So I think it'd be more about parameter changes. I mean, it makes sense that AWS will continue to have a product that offers long-term infrequent access for cheaper than online access. And so having a service that can, an architecture that can take advantage of that should always be valuable.
I'll comment that the kind of stuff that goes in deep archive is data that has an awful lot of hysteresis to it. And so I got Ryan nodding.
Yeah.
Maybe he could finish the thought.
For sure, yeah. So the idea behind Glacier is for that long-term storage and for deep archive specifically for very, very large data sets that need to be stored. So as far as pricing goes, in the 13 years history of AWS, we've had around 100 price cuts where we've reduced our costs. We've never increased any of them. So as the prices change, that might change some of the economics where where it maybe becomes more effective to go ahead and run this more often. Those parameters for the number of restores that are available per petabyte that you're storing, like that might grow to allow you to restore faster and run the train more often. But and then of course, as new products and services get launched, right? If some new container orchestration piece happens, that gives you a new place that you can kind of develop against to where, and what we would kind of envisioned is that for each one of these data sets, we would have a sample sort of CloudFormation template that would give you a place that you can execute your batch jobs, right? You can of course go ahead and take that and customize it to do whatever you want with that. If you wanted to change it to use, say, Kubernetes instead of ECS. Yeah, so there may be additional services that come available that might make some of that easier, that might be preferred. So, the idea behind AWS is that if something is running today, I can't think of any services that we've actually decommissioned. We're actually using a service that we don't highlight anymore, which is actually somewhat amusing. So SimpleDB, if you're an AWS user today, you might have said, wow, I've never heard of that service. That's because we kind of stopped marketing it about 8 years ago. But the reality is that we don't want to have an application that someone has deployed and they're expecting to run for the long term, and say their development staff or the consultant that built it is no longer available to update the APIs to something new. We want to really limit the amount of change that we have to force onto people. So we continue to operate those, and at some point we might sunset SimpleDB, in which case hopefully there's a better replacement, and it's an easy thing. So that's a long answer to jumping in there, but hopefully that's helpful.
I had one more question. So Ryan, I know as a solutions architect, your role is to the Illinois folks come to you and say, this is our concept and we want you to help make it happen. But you're a solutions architect, I'm assuming, for a lot of folks that are dealing with similar challenges, lots of data, and coming up with ideals. So I'm presuming you don't come in and say, guys, this is not the way to do it. Over at Johnson & Johnson or at NASCAR, everyone has big data and these are the solutions they have come up with. But I wonder if you could speak to a little bit, so I know you can't say what all the different ways are, but if you've learned anything, or if there's anything particularly unique about geospatial data or the types. I mean, in some ways data are just data, but in other ways that we like to think our data are special in some way. If you have learned anything working with this type of data that does make it particularly unique, or that you have to develop in a way that's particular to the types of questions that scientists might ask with these data.
Yeah, so that was one of the questions that we had when we were talking about how do we actually bin this data together, and how do we so you'd want to go ahead and make your bundles of data to where that has files that are likely to be accessed in the same sort of batch, right? So that if people ask for different sort of paths or different time ranges, those are the two sorts of things that we were thinking about, to where you can go ahead and you can make it so that if someone, for a particular request, they may only have to get a portion of the data that comes out of that. So, but yeah, as far as how the way that I engage is that I tend to just come and listen to people's problems and then make suggestions about the architecture that's there. And most of the data sets that I come across all have very unique characteristics, right? So so much like the answer about what's the best architecture in AWS, the answer is almost always it depends, because your data set is going to be varied. So for other use cases of the data carousel, it's very likely that we're going to end up finding that there are different packaging strategies that make sense, right? The question that we had about the smaller granular size, if you find that people don't need that full access, then it makes sense to have that be as small as possible. So a full run might end up taking you 3 months to get through, but if people aren't accessing that full data set, and that's really where the analysis kind of comes in, that's useful. So over the course of this project, we actually we started with a little bit of an idea and kind of meandered our way around as we started just kind of collecting and hearing about more of the solution, the problem that we're trying to solve. So and then so yeah, I get to help help developers understand what the various tools are and recommend the best ways to connect them, and then support them as they go ahead and build it. So as a solutions architect, my limit is I can't actually write code in your account for you. So I end up being that support person working between many teams. And yeah, and I should also say that while I do work with universities based out of Chicago, so we have NDAs in place with most people. So unless they actually tell us that they want to be publicly referenceable and are happy to talk to people, we're happy to connect people to share those learnings. But we're also sensitive to secrets.
Well, I think your point of when you're developing something, you're thinking of how people are using it. So the old, things that are close are more similar than things that are far apart that you probably are developing, that people might use granules that are close to each other compared to ones that are on the other side of the globe. So I think just developing with a science question in mind seems to make a lot of sense. So thank you.
And I mentioned that we would see that there's a lot of patterns that emerge from this, right? There might be 2 or 3 sort of for various data sets, and then you end up being able to reuse a lot of the like the CloudFormation templates or the and a lot of that goes as well to how you actually I presume that there's going to be a cost agreement to subscribe to this, just to share some of those, or if it's already fully funded, perhaps that's there. But yeah, that business model, how that might work, likely also is going to be a case-by-case basis. Perfect. Okay. I can keep talking, so I will just stop. Don knows that very, very well.
So yeah, we'd be really love to hear about any ideas people have about other data sets that might benefit from this treatment. Otherwise, we'll keep hacking merrily along. I love how every day is bring your dog to work day.
I certainly want to thank everybody who came, and we're in general very interested in the problem of overcoming cost limitations, and at some level, an approach like this also tries to overcome the risk of taking on the task of serving some kind of data and not knowing how to manage it and which kind of tier and what kind of expense to incur. Because in our kind of community of scientists, people come, people go, interest comes and goes.
All right, I think with that, we'll say thank you very much, and see you around ESIP. Have a great meeting.
All right. Bye-bye.
Thanks, everyone. Have a great day.